Hey, I'm Michael O'Connell. I run the data science team at TIBCO. I work with companies who derive insights from data at rest to drive actions across critical business systems like customer service, machine management, transportation, logistics. Today's case study involves managing industrial equipment, these days heavily instrumented with sensors for monitoring diagnostics such as pressure, temperature, current. We see these sensor data coming off of turbines, manufacturing systems, pumps. Our demo today is around the maintenance of artificial lift systems in oil fields. We analyze sensor data to develop leading indicators for equipment shutdowns, and then we monitor the sensor data in real time to send notifications and alert when thresholds are violated to prevent the shutdowns. So this is a high-value problem. The US is now the leading supplier of oil to the world economy, producing about 10 million barrels of oil a day at $50 a barrel. That's $500 million a day. And in these times of high supply and low margin, it's critical to keep oil flowing to maintain a profitable operation. Today's demo involves maintenance of artificial lift systems in oil fields. Here we see a set of wells in North Dakota, and I'm going to filter into the study wells of interest. Each of these wells we're receiving sensor data in real time, and I can see as I color by failure which of these wells had a failure event in recent data history. I can see the traces coming off the sensors on the pumps for pressure and current relating to the pumps in focus. I can select the wells that have failures and trace their sensor traces, and then I can zero in and investigate a little bit more detail those wells or other wells. I can interactively choose wells to explore the sensor traces in pressure, blue, and current in orange. So let me pick a few wells. I'm going to pick failure conditions on 4 different wells, and I'm going to align those at the point of failure here, the vertical black line, and look backwards in time. So these failures occurred on different wells at different times, but I've normalized to the point of failure and exploring the data leading up to the stoppage. Pressure in blue, a current in orange, and I can see pressure ticking up, current ticking down, some good way ahead of the stoppage. Now, if I were to calculate this a little more quantitatively, I can start to look at the traces of pressure in blue, current in orange, leading up to a failure. The failures, again, are in the black vertical lines. So let me pick a little bit of a window here leading up to this failure, and I'm going to calculate the slope of pressure leading up to this failure event. The software is also going to calculate the optimal threshold, checking the historical data for different failure events that have occurred. So the condition that I've marked has a slope of 26.55, and the grid search around this region produces an optimal slope of 13.275. The actual slope that I've calculated in the historical data led to a shutdown 50% of the time, whereas the optimal slope led to a shutdown 88% of the time. So that's a pretty good true positive rate on the historical data, and I'm pretty comfortable in pushing that as a rule across for monitoring on the real-time system. So I can go ahead and click and send that optimal slope across to the Streambase event processing platform for monitoring real-time data. So we're now in the Streambase event processing environment, and here I can see I'm clicking on this sigma sign here, and I can see the calculations that are occurring across a sliding window, a 6-hour sliding window, where I'm calculating that slope that I just measured in the Spotfire analytics environment. Real-time data is flowing through here on the left. Here's where I've sent the slope from Spotfire into the event processing environment. I'm going to flow real-time data through here, and as it hits this calculation icon, it's going to make a variety of calculations in sliding windows, 6-hour sliding windows. And if that pressure goes above the value that we just identified in Spotfire, I'm going to send a notification. Now, this demo, I'm going to actually send a root cause analysis notification in Spotfire that will send an email to the appropriate engineer with an analysis of the recent data leading up to the threshold. And this threshold, as we've seen on historical data, is able to predict a shutdown about 88% of the time. So the engineer can go and look at this, what's been notified, look at the root cause analysis, and assess what intervention to take. So now let me start up this process. And we're going to now flow real-time data through the workflow. So the data are now flowing through this Streambase application. The rules are being calculated. As the thresholds are exceeded, we're going to send a notification, and we're going to launch a Spotfire root cause analysis. The notification is going to be in the form of an email, and the end user will be able to click on the email to drill into the root cause analysis. Now let me also, while that's going on, I'm going to open a live view onto our live data mart, which is tracking and maintaining the data in a queryable form. And in addition to the notifications we'll get in the email, we'll also be able to see the data as it flows into the live data mart. So here's the wells that were in the study on the map. We can see the pressure here in blue, current here in green, traces of pressure in blue and current in green below. And as one of the thresholds is hit, the well lights up in red, the schematic heat map lights up in red, and we can see which locations are having issues with the pump as identified through the earlier analysis in Spotfire. So the data's been sped up here. Data is typically not flowing through this quickly. For demonstration purposes, we're flowing it through a little faster. Now these notifications that are firing off indicate that the pressure or current threshold has been violated. And we saw in the Spotfire analysis that if the pressure threshold is violated, there's about 80% or so chance of the pump stopping. Now let's cut over and see what's going on in my email box. And I have indeed started to receive some emails with the critical events occurring in different wells. Here's one where I see the pressure has increased, current has decreased at this particular well. So I get a thumbnail of the notification. And I can click here to drill into a more detailed analysis that's been triggered off of the threshold violation. So here, that thumbnail seen in context, I can see a pressure jump, decrease in current, I can see where it occurred, I can see a little bit of contextual data around the event. Now you can configure the root cause analysis with as much detail or as little detail as you would like, including incorporating data from other systems, contextual data about the well, its operations, and history. We've now seen the data flowing through the Streambase event processing system. We've seen that data show up live in our live view onto our live data mart. And we've seen the notifications come through our email client indicating the well that has exceeded the pressure threshold, where it is, and a drill down into a more detailed analysis showing that report that we saw with a little more context around the failure. So our analysis of the sensor data today, we've developed leading indicators for stoppages from historical data at rest. We found that increasing pressure and decreasing current led to stoppages. We were able to capture those sensor diagnostics in models, and we back-tested those to find optimal thresholds. We then were able to publish those models to the event server and monitor sensor data coming in from the equipment in real time and make an intervention when there's a potential imminent problem. So in this way we're able to keep equipment running, and that can create some extreme value in the oil and gas business. So we're seeing operators save upwards of $50 million a year across a collection of assets and equipment that they're monitoring. The TIBCO approach to this is highly configurable. So we're able to develop, implement and iterate models very quickly and apply them to different situations. So operators in different conditions, different environments, different fields around the world, different equipment types, we can set in motion different thresholds and configure the models appropriately for those different situations. So I hope you enjoyed it. Thanks for your time.